Hey everybody, Dr. D. Hope you're well. Last time when we met, we did a practice problem talking about hypothesis testing for a test of two means when sigma 1 and sigma 2 were known. Those are, just to refresh your memory, these are our population standard deviations. And today what I want to do is I want to introduce you to the type of test we would do when those things are unknown, right? When we find a scenario where we don't know what our population standard deviations are. So without further ado, let's jump right into it. As has been the case in the past, if we don't know sigma 1 and sigma 2, what we're going to do is we're going to use S1 and S2 instead. And these are our sample standard deviations. And if that's the case, as has been the case in the past, if we don't know the value of S1 and S2, we're going to have to use a t-test, right? That's going to turn into a t-test. And I did want to draw attention to the fact that this is the case generally, right? Since these are population standard deviations, we generally don't expect that we would know those. If we have the data, we can always find our sample standard deviations. And as a result, this is a very applicable test. It's so applicable, in fact, that in the software I use, Stata, and in many other forms of statistical software, this is the test that is run as the default, right? So if you just type in the word test and then you type in two variables, it runs a two population t-test of means. So this is, and I say this, not being superlative, or I'm not being hyperbolic, I should say. I'm being superlative. This is the most popular test, right? This is the most common, most typical test that you could run. So what does it look like? Well, because it's a hypothesis test, we're going to do exactly what we've done before, which is just go through the 5 steps. So let's start. Step 1, as has always been the case for hypothesis testing, is just to formulate our hypotheses. As in the past, we're going to have a null. We're going to have an alternative. And then, just like the previous case we just dealt with, right, with two means where sigma 1 and sigma 2 were known, we're going to test a difference between two population means, mu1 and mu2. Like, that's what we're looking at, mu1 minus mu2. And then we're going to have some symbol that goes here. It's going to be, like a binary relation. And on the other side, we're going to have some value, call it d0. Now inside this box, we could have a greater than or equal to sign, or a less than or equal to sign, or an equal to sign. And then down here, we would have the corresponding relation, right? Less than or greater than or not equal to. And then this value right here, this d0, that is going to be, that's our difference under the null, or our hypothetical difference, right? For the sake of argument, how different do we think these two population means are? And in most cases, in most applications, this is usually 0. That's because if it's 0, then we're just testing, are these things the same or are they different? And often what we want to know is, we have got two populations, as we discussed, they're different in some visible and easily observable way. Are they also different in some other way, looking at this variable? You could put a number there if you wanted to see if the difference was more than a certain value, but you don't have to. Anyway, step 1 is done once we've stated these. Step 2, as has been in the past, is to choose a level of significance, which is we'll call alpha. As we've said in the past, that's like a belief parameter. Alpha is a common Greek letter to use here. And this alpha, typically, the most common is 0.05. But you might see 0.01, you might see 0.10. Those are also common values. All right, step 3 is to choose a test statistic. I think this is the 5th one that we've learned. If we're choosing a test statistic, the way I like to think about this is as a decision tree. So let's say that we've got a bunch of tests where we're testing one population, and now we're looking at tests where we're testing two populations. So far, what we've learned about with the prior test and this one are both cases where we're testing mu1 minus mu2. That's the thing we're trying to measure here. We're trying to make an inference about. And if that's the case, we either know our sigmas or we don't, and we just have our s's. So in the scenario where we've got a test of two populations, and the thing we're testing is mu1 minus mu2, and then we have our s's instead of sigmas, right? Where we're going to go then is this particular t statistic. It's going to look like this: t equals x bar 1 minus x bar 2 minus d0 over square root of s1 squared over n1 plus s2 squared over n2. And this should look familiar because it's similar to our z statistic we had for two means, with the difference just being that z has been replaced by t, and our variances have been replaced by sample variances, right? Our standard deviation sigma was replaced by our sample standard deviation s. And so it's a t-score instead of a z-score. And as a result, under the null, it's going to have a t-distribution. Now, in the past, when we've looked at t-distributions, the number of degrees of freedom was n minus 1. In this case, that's not the case, right? We've got two different samples here, so there's no, which n are we going to use? And I'm going to warn you, this is the ugliest formula we're going to see all semester. We're going to have to calculate degrees of freedom using a formula. And that formula looks like this. Degrees of freedom, so where degrees of freedom equals s1 squared over n1 plus s2 squared over n2, the variance there squared. And then on the bottom, we're going to have two sides. On the left side, we have 1 over n1 minus 1 times the quantity s1 squared over n1, that quantity squared, plus, and then on the right side, we've got 1 over n2 minus 1 times the quantity s2 squared over n2, that quantity squared. And it ain't pretty, I'm not going to lie. It's not terrible, but it's not great. But I do want to point out that it's not as hairy as maybe it looks. This part right here, this is the same as the thing inside the radical here. So if you're calculating piecewise, like step by step and keeping track, you don't have to recalculate these because these are the same numbers. Similarly, and this is the variance of the difference, right? Variance x bar 1 minus x bar 2, sample variance there. Similarly, this right here, that's the same as this, which is the variance of x bar 1. And then over here, this color maybe, got this thing right here, which is the same as this thing right here. So we're reusing some parts here. That's the variance of x bar 2. We're reusing some parts. That'll save you a little bit of calculation. It's not going to save you a ton of time, but better not to have to recalculate if you don't have to. And so that's that will give us a little bit of savings. Mostly you just have to be careful, take your time, make sure you do the thing right. Now the one thing I want to point out is that degrees of freedom have to be an integer, and this is not. There's no reason to expect that this would, generally speaking, yield an integer. So we're going to need to turn it into an integer, and in this case, it turns out that whatever value we get here, it's going to be rounded down. Then that's not generally true. Most of this class will round the way you learned. But in this case, for degrees of freedom for a t statistic of two means, we're going to round down this fraction to get our degrees of freedom. And the nice thing is that Excel knows this. So if you give it the decimal, if you just give it the value that this fraction evaluates to, Excel will just cut off the decimal part. So, but it is the case, right? If you got like 17.9791, that turns into 17 degrees of freedom. So that's what I mean by rounding down, right? We're going to just ignore everything after the decimal. And so that's how that works. That's the test statistic. Just like in the past, once we've chosen our test statistic, this thing right here tells us what we need to calculate for step 4 to compute. And so we would do that. And then this right here, tells us what we need for step 5, right? Which curve are we going to draw? And so step 4 is to calculate this, right? We take our x bars and our d0 and s1 squared and n1 and all that stuff. We calculate the value of our t. And then in step 5, right? In step 5, what we're going to do is we're going to draw ourselves a t distribution with the correct number of degrees of freedom. And then based on where our test statistic falls, we're going to have to find the area under this curve, right? Because that's how we would get a p-value. We need to use this curve somehow to get a p-value. So what can we do to try to get a p-value if we have a t statistic? Well, what we've done in the past, and you can continue to do this, it will still work. Once you get to a t-distribution, it doesn't matter what path you got there by, you can use the T.dist formula to find, you put your t in here, and then your degrees of freedom, and then 1 for cumulative. This will always find you the area to the left of your t. Which then you can use manipulation to try to get what you need out of that. You don't have to do it that way, and we've been doing this for a little while. I figure I'll give you some alternatives if you prefer. If you want to, you can use T.dist.rt, right tail, t comma df, and this will give you the area to the right. It's a shortcut for certain applications. Maybe you want it, maybe you don't. And then finally, if you want, there's also a two-tail analog, 2t. I don't love this one. This is the two-tailed area. I'll tell you why. It is the case that if this last one, this 2t1, you have to feed it a positive number. That must be positive, or Excel throws an error. So when I use this one, and I do occasionally use it, I almost always put the absolute value of t nested inside this formula. That way, depending on what my t statistic kicks out, it's not touchy, right? I want it to be robust to whatever t I get. Because what if I got a positive t and then I realized I did something wrong and I changed the numbers? If it turns into a negative t, then my p-value is going to give me an error, and I really don't want that. So whenever I do that, I use the absolute value. Just so you know, you don't have to learn this one. You don't have to learn this one. Those are bonus content. But if you want to, nice shortcuts if you feel comfortable. Want to learn some more Excel. Okay, once we have our area, the correct area, we get a p-value. Then what we have to do is we have to compare our p-value to alpha, right? And if it is the case that our p-value is less than alpha, then that means that we reject the null and accept the alternative. On the other hand, if we've got a p-value and alpha such that p-value is greater than alpha, then we would fail to reject the null. And those are the two options that we can conclude, two conclusions we can come to. In that case, it's an inconclusive test. Okay, so this is a scenario where we have two populations from which we're drawing data, and we want to observe them and find out whether some underlying value in them is statistically differentiable, which is to say they might be different in the sample, but that could just be noise. Are they different enough that that we can conclude that the population values themselves must be different? And this is the tools we'll use in the cases where we don't know what the population standard deviations are. It's a very commonly used test. It's very powerful, and so it gets used a lot for that reason. Yeah, I hope you found this useful. If you have questions, as always, get in touch. When we get together next time, I'm going to go through a practice problem with one of these so you can kind of see how these not uncomplicated formulas work themselves out. Thank you. As always, get in touch with questions, and I'll see you next time. Bye.